We're going to work a few examples on growth and decay. Some may be familiar, some may not. So we'll revisit something we talked about in AP Prep about continuous interest. So our situation is an account earns 3% of the current balance per year, and the initial investment is $1,000. So this is actually saying that the rate of change, the growth rate, is 3%, and we can see it's proportional to the amount that is present. So we may not have thought of this before, certainly not in AP Prep, but what we're saying is that the growth rate, the rate of change, is proportional to the amount present. And in fact, we even know what the K is in this case. Since we know it's growing at 3%, we have dp dt is equal to 0.03 times p. So there's our differential equation. Since we are also told that the initial investment is $1,000, we can add to that the initial condition that p of 0 is 1,000. So this is our differential equation together with its initial condition. So then we can do part B. We can solve it as we've seen before. We can divide the p over to the dp side, leave the 0.03 on the other side, and multiply the dt to the right side. We can then integrate both sides, and as we've seen many times before, we'll get the natural log of p will equal, in this case, 0.03t plus c, the constant of integration. We can exponentiate both sides and get to p is ce to the 0.03t power, which you may remember from your AP Prep days as APERT, or the amount is equal to the initial value p times e to the rt, where the r is that continuous interest rate. We can continue on and use the initial condition, p of 0 equals 1,000, and say that p is 1,000 when our time is 0. And so that's going to tell us that the initial amount is 1,000, and our p of t, or p, is 1,000 e to the 0.03t. So a calculus way of looking at maybe familiar continuous interest APERT problem from earlier. So let's do another example. We're going to talk here about half-life, and so we have seen this at various times in the past, and this is also an example of our differential equation where the rate is proportional to the amount present. So we'll say in our situation, the half-life of radium-226, so I'll say radium-226 is 1,590 years. A sample, so we're going to look at a sample of, and then we'll abbreviate that as RA for radium-226 is 100 milligrams. So first what we're going to try to do is to write an initial value problem, which I'll call IVP. So that means we want a differential equation, and then we want to get some initial conditions if we can. So the amount present, or the rate of change rather, of the amount of that radioactive material is going to be proportional to the amount present. We also know that the initial amount at time 0 is 100 milligrams, and we also know that the amount present in 1,590 years is going to be half of that initial amount, 50. So there is our initial value problem, the differential equation together with the initial conditions. So secondly, part B, we're going to say find a formula for the mass of that radium-226. So I'll say for the mass of Ra-226 after T years. So in effect, what we're going to get is a formula for the amount present in terms of T. Well, we've done this a few times before. We can divide the P over with the dP. We can multiply the dt to the K side. We can integrate both sides and get the natural log of the absolute value of P is equal to KT plus C. We can exponentiate both sides and get P is CE to the KT. So there's our general solution. We have a couple of initial conditions. We need two so that we can find both C and K. So using the first one, P of 0 equals 100, we can say 100 is going to be CE to the 0, and so that means that the C is going to be 100. So that leads us to P equal to 100 e to the KT. And we can then use the second initial condition and say that 50 will equal the 100 e to the, and we don't know what K is, but we're going to use 1,590 as the value of T, because in 1,590 years, we're going to have half of what we started with. So we'll divide by 100 and get 1/2 is equal to e to the 1590k. We'll take the natural log of both sides, and that will give us something that looks like this. We can do all kinds of properties of exponents here. Who could resist saying that the natural log of 1/2 is the natural log of 1 minus the natural log of 2? On the right side, we know that a logarithm base Euler's number and an exponential base Euler's number are inverses, and so they will cancel. We also recognize that the natural log of 1 is 0, and so when we divide by the 1590, we're going to get k is equal to the negative natural log of 2 over 1,590. And we're probably not surprised, if we think about it a moment, that k is going to be a negative because this is decay. We know that the amount is going to be decreasing over time. So we'll do part C. How much will there be? How much of that radium-226 will there be after 1,000 years? So how much Ra-226 will remain after 1,000 years? So we will use our formula, which, I guess I should have said more clearly that then, well, I think we're okay with that since we said what the K and the C are. So we can go with, we want to know how much will there be after 1,000 years. And so we have our 100, and then it's going to be e to the, and you're welcome to put that into your calculator. And we're going to take the, if you want, so that's negative natural log 2 over 1590. That's our k, and we're plugging in the 1,000 for our value of t. And then it's going to be just a calculator problem, and we can say that's going to be, you can check on this, but that's going to be approximately 65 milligrams after that 1,000 years. And so the last part of this problem is we want to know how long will it be until 30 milligrams remain. How long until 30 milligrams of that Ra-226 remain? So in this case, this is our value. The 30 is our value for P. So we're going to plug the 30 in. we've got the 100 e to the whatever that negative natural log 2 over 1590 times t is, and we can solve this now for the t. So we can divide by the 100, and 30 divided by 100, I believe, is 0.3, and that's going to be our e to the negative natural log 2 over 1590 times t. We'll take the natural log of both sides again. So there's our natural log of 0.3, and on the other side, when we take the natural log there, the exponential will cancel, and we're going to get negative natural log 2 over 1590 times t is the natural log of 0.3, and then we'll divide by that negative natural log 2 over 1590. And I believe if you then put that left side into your calculator, you're going to get, let me make that even a squiggly or equal sign. We're going to get approximately 2,762 years. Okay, so there's a half-life problem. I'm going to do one that is probably, I would think, unfamiliar, and I don't know if you guys do this if you're in physics or not, but this has to do with what's known as Newton's law of cooling. So this is another example for us to use growth and decay. So our problem is going to be if capital T, this is going to be you have to be a little careful because I'm going to use T's to be two different variables. So if capital T is the temperature, let me get my pen to work, is the temperature of an object at time, and then I'm going to use little t for the time variable. So you got capital T is temperature and small case t is time. And I'm going to say that capital T sub s is the temperature of the surrounding media, is the temperature of the surrounding media. Now, talk about what this means here in a moment. Then what we get is that d capital T, d little t, so that's the rate of change of the temperature with respect to time, is going to be some constant times the temperature of that object minus the temperature of the surrounding media. So, for example, if you take a hot cup of coffee outside in the middle of winter, the capital T is going to be the temperature of the coffee, and the capital T sub s is going to be the temperature of the surrounding air. So you can see that it's going to the change in temperature will be some constant times the difference between the temperature of the cup of coffee and the temperature of the cold air. Or likewise, it could be something that's cold. So if you take a cold, say, Pepsi outside in a hot summer day, then you can see that the temperature of that cold Pepsi is going to change at a rate that's proportional to the difference between the temperature of the cold Pepsi and the warm air around it. So given that we have a hard-boiled egg, we're going to talk about a hard-boiled egg at 98 degrees centigrade. 98 degrees centigrade is put under running 18 degree centigrade, or Celsius if you rather, water. After 5 minutes, The egg's temperature is 38 degrees. And we want to know how much longer will it take for the egg to reach 20 degrees Celsius. How much longer will it take for the egg's temperature to reach 20 degrees? So let's see what our differential equation looks like. We're going to look at this dt, d capital T, d little t is equal to k times capital T minus T sub s. So we've got the change in temperature with respect to time is going to be some unknown constant that we're going to have to figure out somewhere along the way here. Capital T is the temperature of the egg, and the surrounding media is going to be this 18 degree water. So we're going to go T minus 18. We also know that the temperature at time 0, that's going to be that 98 degree egg, so it's going to be a 98. So we know the capital T of 0. We also know that the temperature at time 5, so 5 minutes afterwards, the egg's temperature is 38 degrees. So we know that T of 5 is equal to 38. So there's our initial condition. So now we can go to work on solving this. We're going to separate our variables. So this is an example of one of those where we can't separate the T from the 18 initially. We're going to have to divide that whole thing over. So it's going to look like 1 over T minus 18 d capital T is going to equal K times the little dt on the other side. We'll integrate both sides, and so that's going to lead to the natural log of the absolute value of T minus 18, and that's going to give us KT plus C on the right side. We'll, as we have before, exponentiate both sides and get capital T minus 18 is going to be C e to the K little t. So there's our general solution. And now we're going to use some of our initial conditions. So using the T of 0 is equal to 98, we're going to get that 98 minus 18 is going to equal C e to the 0. So that is going to tell us that the C is going to be 80. So now we know a little bit more. We've got, so I'm going to come here and I'm going to say T equals, I'm going to add the 18 to the other side. That's going to be plus 80 was our C, and we still have e to the KT, and we still need to solve for the K. So we'll use our next initial condition. So now we're going to use the T of 5 equals 38. And so if we plug in the 38 for the T, and then we've got 18 plus 80, and then e to the, and we're plugging in 5 for the T, so that's going to be a 5K. And we're going to solve this thing for the K. So subtracting the 18 over gives us 20 is equal to 80 e to the 5K. And dividing by the 80 is going to give us 1/4, I believe. 20 over 80 is 1/4, equal to e to the 5K. We can take the natural log of both sides. Oh, I can see we're going to get to use some of our properties of logarithms again. I always get kind of excited by that. Natural log of 1/4 we know is natural log 1 minus natural log 4, and the natural log of e to the 5K is going to be just 5k. We know natural log of 1 is 0, so if we divide by 5, we're going to get negative natural log 4 over 5 is equal to k. And so that makes our equation for the temperature, T is equal to 18 plus 80 e to the, and we've got this negative natural log 4 over 5 times t is our equation. And the last thing we're trying to find is when is that going to be, how much? 20 degrees. So we will say 20 is going to equal 18 plus 80 e to the negative natural log 4 over 5 times t. And we're solving that for the t. And if you subtract the 18, I think we get 2 is equal to 80 e to the negative natural log 4 over 5 times t. And dividing by the 80 is going to be like a 1/40th equals e to the negative natural log 4 over 5 times t. We're going to take the natural log of both sides and then divide by the negative natural log 4 over 5. And I think you're going to get that t is going to be about 13.3 minutes. But remember, the question we were asked is, what was our question? It says, how much longer will it take to reach 20 degrees after the 5 minutes it took to get to 38? So when t is 13.3, that's going to be another about 8.3 minutes. So about 8.3 minutes more to reach that temperature of 20 degrees. All right, very good. Hope this is some help.